The idea of second derivative test is to approximate the surface of the graph of a function by their Taylor polynomial of degree 2 near a critical point. So here I have a critical point. It's obviously a local min, and I want to approximate that with the Taylor polynomial around that. And that Taylor polynomial is a paraboloid that looks like this, basically looking upward. And if I have basically a local max over here, I can again approximate with the Taylor polynomial. It would be looking downward. And you can guess that if you have a saddle point again, the Taylor polynomial will look like a saddle point. It will look like a hyperbolic paraboloid. So let's talk about second derivative test. Second derivative test is a way to find local extrema. Let's start with the second derivative test. The second derivative test is a way of finding local extrema or saddle points of a function of two variables, f of x and y in our case, and it uses the discriminant of f at a critical point a and b. Discriminant of f at a point a and b is going to be the pure second derivatives multiplied together minus the mixed second derivatives multiplied together. And you can notice that because second derivative test requires a certain amount of differentiability, you don't have to assume that f sub xy is different from x sub yx. So if the discriminant is positive, you can use your second derivative test from calculus 1 and just use f sub xx and f sub yy to figure out if you have a local min or local max. And if the discriminant is negative, then you will have a saddle point. Discriminant equal to 0 is inconclusive test for us, basically, for the critical point a and b. Again, there's certain rules that we have to follow for the differentiability, and having the second derivatives all to be continuous as well. What is happening in here is that, again, as we said, we are approximating using a Taylor polynomial of degree 2 of the second degree. And we are assuming that at least one of the second derivatives is not 0. If all of them are 0, the discriminant is going to be 0, so it's not as interesting. Now, let's say that a and b is a critical point of f of x and y, and f has convergent Taylor series in a second degree polynomial approximation of f about a and b looks like this. And you can draw this by a little knowledge of Taylor polynomial of second degrees. What happens is I put in a 0 over here and a 0 over there. What I want you to know is that this is not typically 0. It's just because a and b is a critical number of a critical point of f. These are going to be 0. Now that we have that, the other thing that I want to do is, this was very busy. Thankfully, being critical point, get rid of this term and that term. And now what I want to have is not to have x and y shifted. So I don't want everything to be shifted to point A and B in this. And so what I do is I shift everything back, A, B, and f of A and B back into 0 and 0 and 0. And that gets rid of this. It gets rid of A and B over here. And it will look like this, basically. So now that I'm looking at this, I see that after all shifting, everything is done. I have a term with x squared and a term with xy and a term with y squared. And this is a quadratic surface, basically. And so the Taylor polynomial of the bigger function f of x and y turn out to be a quadratic surface for me. And so I have to figure out what quadratic surface that is. It's a quadratic surface, and I'm not very familiar with x times y term, because all the quadratic surfaces we talk about are in standard format, and this is something new to us. But it turns out that are going to be the paraboloid of some sort, basically. Now, what I want to do is to use the completing the square to recognize these quadratic surfaces. And it's just that A and B and C that are based on second derivative value of A and B. I want to figure out how changing A and B and C changes my quadratic surface, basically. Now, let's say if A is 0, B is not 0, and C is 0, then Z is going to be equal to bx times y, which is going to be a hyperbolic paraboloid. We're going to show you this at the end. In this case, discriminant is going to be negative. If you go back and find a discriminant, it would be a negative, and it matches the test. So let's assume A or C are not 0, and then from there, I start with A not equal to 0. Symmetrically, C not equal to 0 gives me the same thing. I complete the square, and after completing the square, let's say I complete the square between x squared, because A is not 0, I can factor it out, and then there will be a leftover. The leftover is going to be in terms of a y squared term. And computing the leftover, I get this r. We've done a lot of completing the square, so this should work well for you guys. And then that's just by expanding the first part, and I figure out what the leftover is. Now, roughly I will have, how many cases? I will have 3 cases. So one thing I want to say is that now you see the y squared is here, but you don't see an x squared in here, because the axes have turned a little bit. This is the axis kind of rotated, so there's a new axis over here, and that 2 power 2 gives me that new axis. Basically, they may not be orthogonal to each other, but there is another axis in here. And so what we have is that again, this new variable for that axis and y squared, they have the coefficient A and this r coefficient, which is some terms. If the two coefficients are the same sign, I will get elliptic paraboloid. If the two signs are different, I get which is this, basically, I get the two signs are different, I get hyperbolic paraboloid. That's a saddle point. And if it's 0, then polynomial is going to be a parabolic cylinder, and it's a second degree polynomial, and it doesn't give us enough information using the test, basically. So I have to use something else, and you will see that in another shape, basically. And again, bigger than 0 is just going to tell me that the signs are the same, and I'm going to get elliptic paraboloid. Elliptic paraboloid means either paraboloid looking upward or downward, local min or local max, and less than 0 means hyperbolic paraboloid means a saddle point. Now, that said, if C is not equal to 0, you get the same routine of completing squares, and you get the same cases, and you end up with the same situations that every case follows the second derivative test that we defined in the beginning, basically. And so in mathematics, we don't typically show the case C not equal to 0, because A not equal to 0 and C not equal to 0 are very symmetric. We say just without loss of generality, that's what it is. And so one other thing that I want to say is that r times A that we did, which is going to be AC minus B squared over 4, is exactly a fourth of the discriminant. So when I was saying that r times A is bigger than 0, I was just saying 1/4 of the discriminant is bigger than 0. And when I was saying r times A is less than 0, 1/4 of the discriminant. And similarly, when it's equal to 0. So everything that we did was justified. Then what we didn't cover in here was that when A is equal to C equal to 0, when discriminant is going to be negative B squared and is less than 0, and the Taylor polynomial Z equal to B times XY is a hyperbolic paraboloid. Now let's show this on for different values of A and B and C on GeoGebra for a quick minute. So one way to kind of visualize what we just said is that we're going to simplify the function locally, to a shape ax squared plus by squared plus c times xy. That's the Taylor polynomial right there. And then depending on what a and b and c are, which a and b and c are related to the different second derivative values at the critical point, you get the different shape. So what you right now is seeing is that with the values that currently is assigned to a and b and c, we have a paraboloid looking downward. I can move this around a little bit more, and you see that I see the saddle point. And before moving on from saddle point, you can tell that at some point it becomes a parabolic cylinder, and this one's looking downward. And again, that's when it's almost there, right? It's not exactly. I'm getting close. I have to move this around to get that 0. And then it changes things, and then we can again go back and come up with another elliptic paraboloid looking upward. And these are all the options that I can get. Again, sometimes when the discriminant is 0, I don't know what I'm getting. I'm getting that cylinders, and it could be looking downward or upward. And this is something good for your lab sections.